Imagine a world where the biggest obstacle to merging humans and machines isn't the technology itself, but your own immune system. We can create brain implants, glucose sensors, and smart drug depots, but the body often responds to all of them in the same way. It walls them off. This silent defense mechanism is one of the most persistent unsolved problems in biomedical engineering. The immune system's reaction can turn even the smartest devices into isolated, ineffective tools. Let's explore why this happens and what it means for the future of medicine. In science fiction, implants seamlessly merge with the human body. Neural implants enhance memory, sensors monitor health around the clock, and devices integrate as if they naturally belong. But in reality, the body treats most implants as invaders. This reaction, known as the foreign body response, limits some of our most advanced technologies. The dream of effortless human-machine integration is challenged by the body's natural defenses, making the journey from fiction to reality far more complex. When an implant is placed in the body, the immune system springs into action. First, it detects the foreign object. Then inflammation begins and cells gather around the device. Eventually, fibrous tissue forms a barrier, literally building a wall around the implant. This process, called fibrosis and immune isolation, can degrade signals, block sensors, reduce drug delivery, and ultimately cause device failure. The body's protective instincts create a major challenge for engineers and doctors alike. This problem affects nearly every implantable technology. Neural implants, for example, see their signals degrade over time as scar tissue forms around electrodes. Glucose sensors lose accuracy because proteins and cells accumulate on their surfaces. Pacemaker leads face fibrotic encapsulation, which can interfere with long-term performance. Drug depots become unpredictable when surrounded by tissue barriers. These real-world examples show how the body's response can undermine even the most advanced medical devices. Even as closed-loop systems and smart therapies advance, they depend on reliable sensors and interfaces. When the body isolates a device, signals become noisy, measurements unreliable, and feedback control fails. This means your smart implant can quickly become a blind implant, unable to perform its intended function. The body's defense mechanism is a huge limitation, holding back the potential of medical technology to transform healthcare. From the body's perspective, this defensive behavior makes perfect sense. Any foreign object could be a pathogen, a toxin, or a threat. The immune system responds aggressively to protect you. Unlike drugs or temporary treatments, implants are permanent, so the response becomes chronic. The body's vigilance is a double-edged sword, protecting you, but also making it difficult for life-saving devices to work as intended. Real engineering challenge is asking the body to accept materials that are synthetic, mechanically different, and chemically unfamiliar. This mismatch triggers inflammation. Even materials labeled biocompatible often just mean less harmful, not invisible. Engineers must find ways to bridge the gap between human biology and artificial materials, a task that is far from simple and requires constant innovation. Despite decades of research, implant rejection is still not fully solved because it's not just one problem, it's many. Protein fouling happens when proteins rapidly coat implant surfaces within minutes. Cell adhesion means immune cells stick, activate, and trigger inflammation. Fibrosis creates a dense capsule that isolates the device from surrounding tissue. Infection risk is also high, as implants can become surfaces for bacterial growth. Each challenge requires a unique solution. Cutting-edge biomedical engineering is tackling these issues with innovative solutions. One approach is designing anti-fouling surfaces, materials that resist protein and cell attachment. By preventing the initial coating of proteins and cells, these surfaces help keep implants functional for longer. This is a crucial step toward making devices that the body doesn't immediately try to isolate or destroy. Another frontier is immune modulatory coatings. Instead of simply avoiding the immune system, these coatings actively control it. By modulating immune responses, implants can reduce inflammation and minimize tissue barriers. This approach represents a shift from passive to active strategies, aiming to create a more harmonious relationship between the device and the body. Economatching materials are designed to be as soft and flexible as human tissue, reducing irritation and chronic inflammation. By matching the mechanical properties of the body, these implants are less likely to trigger aggressive immune responses. This innovation is helping to make implants feel more like a natural part of the body, rather than a foreign intruder. Dynamic and soft implants are another exciting development. These devices can change their properties once inside the body, adapting to the environment and minimizing immune reactions. By becoming softer or more flexible after implantation, they reduce the risk of chronic inflammation and improve long-term performance. This adaptability is key to overcoming the body's natural defenses. Predictive models, powered by AI and data, are helping researchers anticipate how a patient's body will respond to implants. By analyzing individual biological factors, these models can guide the design of personalized devices and coatings. This approach is making it possible to tailor implants to each patient, increasing the chances of acceptance and success. If we solve implant biocompatibility, we unlock long-lasting neural interfaces, reliable closed-loop drug systems, continuous biosensing, and true human-machine integration. Closed-loop medicine, brain interfaces, and wearable implants all depend on overcoming the body's defenses. Without these breakthroughs, the technology cannot scale or reach its full potential. Instead of saying implants are advancing fast, the real story is that your body is still better at rejecting technology than we are at integrating it. This powerful reframing highlights the ongoing struggle between engineering and biology. It's not just a hardware problem, it's a biology problem. The immune system remains a formidable opponent, shaping the future of medical innovation. Future of medicine isn't just about smarter devices, it's about devices the body accepts. Not fights, not isolates, not destroys. Until we achieve this, every implant is a negotiation between engineering and the immune system. Right now, the immune system is still winning, but ongoing research and innovation are slowly tipping the balance. Every implant represents a negotiation between engineering and biology. Engineers strive to create devices that perform reliably, while the immune system works tirelessly to protect the body. This ongoing battle shapes the development of medical technology and determines which innovations succeed or fail. Despite remarkable progress, the limitations imposed by the immune system remain significant. Many implants fail over time not because of technical flaws, but because the body refuses to accept them. This reality underscores the importance of biocompatibility and the need for continued research in biomedical engineering. Understanding the real challenges behind biomedical innovation means looking beyond the hype. The journey to true human-machine integration depends on solving problems like implant rejection. Researchers, engineers, and doctors are working together to develop new materials, coatings, and predictive models that can finally bridge the gap. The promise of human-machine integration is immense, but it hinges on the body's acceptance of implants. Only by addressing the biological challenges can we realize the full potential of smart devices, brain interfaces, and wearable technologies. The future depends on making peace between engineering and biology. As we look to the future, the negotiation between engineering and the immune system will define the next era of medical innovation. Solving the biocompatibility crisis is essential for scaling new technologies and improving patient outcomes. The immune system may still be winning, but every breakthrough brings us closer to devices the body can truly accept.